sent to you. My email is also here. If you have any questions, you can always email me. And we did this webinar last month, and we ran into some technical problems. Unfortunately, that's why we are repeating it. The cloud was not working at that time, so we got it working again. So I'll do some demonstrations of the cloud, the Nirva cloud, basically. And for this reason, we also increased the time of the talk from 1 hour to 1.5 hours so that we can take our time to explain different features. So let's move on. So what are we talking about today? First, we talk about some differences between the near IR and mid IR, and there are different in many ways. There are pros and cons for each one. And then we talk about the need for a portable NIR spectrometer in various applications. Then I would move on to explain the digital light processing technique that Nirvascan uses and compare it with the linear array detector method. Also, I'll introduce different models of Nirvascan, which are reflectance, transmittance, and fiber optic in the standard and extended range. I'll show you how to record a reference. And then we go into some case studies. And these case studies involve chemometrics. For example, sweetness of fruits in grapes and measurement of protein and moisture in wheat kernels. And then I'll go into the Nirva cloud and demo Nirva cloud for probably about half an hour. Different features, how to build a model, how to pre-process the data. And I find that this is very useful for understanding of how to work with Nirvascan. So you need to be able to do chemometrics, and you need to be able to use the cloud effectively. And so that's why I'm demoing it. Finally, we get into some case studies on the reflective unit and the transmittance unit, and also the fiber optic unit. I'll demonstrate these. And then there is a flow measurement proposal, and the app, and the Nirvascan in scientific literature. These are the topics that we'll be covering in this talk. So let me activate this mouse here. So pointer options laser. Okay, so over here you see the electromagnetic spectrum, and you can see that the near infrared is part of the infrared spectrum from 780 to 220 to 2500 nanometer, or 2.5 micron, sitting right next to the visible region. You also have the mid IR from 2500 to 25,000, and the far IR from 25,000 to 1 millimeter, basically. So what happens is that the molecules, they have these vibrations, and different molecules such as CO, CH, CN, and NH, they have these vibrational modes, and they absorb radiation falling on them. So these vibrational absorption are very strong in mid-IR, and that's why the fundamental absorptions happens in mid-IR. But you can also get the overtones and basically combination bands in the near IR region. So if you look at this diagram, you see the fundamental vibration in mid-IR is about 3 micron, or 3300 wave number. And you have the first overtone, second overtone, and third overtone in the near IR region. And the strength of these bonds basically keep on decreasing as the number of overtone increases. So we will take advantage of this because mid-IR has certain disadvantages. It cannot be used when sample contains too much water. So for food analysis, mid-IR is not a good choice. And also, it requires some expensive equipment and windows. And it's mostly used for petrochemicals and polymer identification. Whereas the near IR is a fast method that doesn't require any sample preparation and can be used for watery materials and food products. and it's easier to use for monitoring products. So the near IR has also disadvantages that there are basically the resolution is not as high as mid IR, and you need some data processing to understand the different bonds for near IR. So to explain this a little bit more, we can compare the diagrams for mid IR emission spectrum here, and this is an absorption spectrum for near IR. So the mid IR is high resolution, and it has strong signals, as you can see, for different molecules here. Whereas in the mid IR, it's a combination of overtones and combination bands, and it doesn't have high resolution. So you need to use chemometrics, some statistical method to evaluate the spectrum to assess what's going on there. Here is the absorption band diagram for the near IR, all the way from 700 to 2500. Of course, the near IR actually starts from 780, but we included 700 here too. So you see different bonds such as CH, CH2, CH3, OH here. They exist here, and NH, for example, for protein you need NH, for moisture OH, for carbon, for sugar and fat, cholesterol, things like that. You need CH bonds. So they occur in all of these regions, and our main spectrometer, the Nirvascan standard method, the Nirvascan standard spectrometer covers the 900 to 1700 nanometer region, which mostly work in the second overtone. We also have the extended model from 1300 to 2100, which works mainly in the first overtone region. And there's also a super extended model from 1600 to 2400 that uses combination band region. The price of the spectrometer increases as we go to the first overtone and combination region. The most economical model is the Nirvascan standard that works in the second overtone region. So you can detect all these bonds in every region. However, in some of the regions, you have some bonds that do not exist in the others. Like in the first overtone, you have the sulfhydryl group SH that doesn't exist in the second overtone. And you also have the POH bond here, again, that doesn't, the phosphorus hydroxide bond that doesn't exist in the other regions. So most of the bonds are repeated in every region, but in some cases there are also some bonds that do not exist in the other regions. So in that case, the extended Nirvascan would be more useful than the standard Nirvascan. So using these bonds and measuring the absorption, you can basically give the advantage to the near IR technique. This is fast and non-destructive and requires no sample preparation. And it can also be used for identifying, monitoring, quantifying, sorting many materials in different industries, especially in food industry and also plastic industry for sorting. So let me talk a little bit about the digital light processing technique. This is a technique that Nirvascan uses, and it's different from the normal array detector technique. So on the left side, you see a typical spectrophotometer that uses a detector array, in-gas detector array. And here you see the lights shining on the sample, is collimated, diffraction grating, sends each of the wavelengths to different pixels on the array. This is how it's normally done. But in the digital light processing method, we have replaced the detector array with the DLP micromirror array. And these are very tiny micron-sized mirrors. And instead of detector array, we have a single point in-gas detector. So the mirrors turn one by one towards the detector, and once they turn and then they turn away, and next one turns towards and then it turns away. So here in the diagram you can see the green is turned towards the detector and is detected. Then this one turns back, and next the yellow would go through. So bit by bit the spectrum is built. And this has certain advantages, and the most important advantage is that without compromising the quality of the spectrum, you would reduce the cost of the instrument, because the detector array is very expensive and the DLP micromirror chip is not as expensive. So you could replace the detector array with a single point detector and a micromirror array. Also, because this is a single point array, a single point detector, you could increase the size of it, and that would improve the signal to noise ratio. And you can also choose different patterns for scanning, whereas here you have to detect everything. Here you can only program certain mirrors to turn towards the detector and only choose those to perform the scan. Of course, there are some disadvantages too, and one main disadvantage is that for detector array you can see a live spectrum because everything is detected at the same time. But for DLP method, you need to build the spectrum bit by bit. So this way, it will take longer to record the spectrum, and you would only get a snapshot of the spectrum at the end. You would not see the full spectrum live, basically, the way you do with the detector array. Speed is also another factor if you're looking for, basically conveyor belt measurements. This would work, but in this case, it's too slow for a conveyor belt measurement. If a product is moving with certain speed and you want to measure its transmission, and it would not work in this case. So there are always pros and cons for each case. But in most of the situations, the DLP would be a very economical and high quality spectrometer to buy. This is basically structure of the DLP. There are two lamps, which are halogen tungsten lamps at 45 and 135. There's a sapphire window, slit. Here's the grating, the DMD board, and then the detector, single point detector, basically. So that gives you an idea of what it looks like inside the spectrometer. So we offer the standard model in three different models, basically. The reflection model here, which is our most popular unit. It has a sapphire window you can see over here. And this is used for grains and solids and kernels and powders, basically. And then you have the transmittance model that comes with a cuvette holder. You have to purchase the cuvette yourself. And this is for liquid measurements. And then you have the fiber model that doesn't have any internal lights. So this is usually used with a reflection probe. So you need to buy an external source, 2x1 reflection probe, and one input goes to the spectrometer, the other input goes to the light source, and then the output goes to the sample. So this way you would use this model to measure. The resolution of the spectrometer is 10 nanometer, but you would get interpolated values at 3.5 nanometers, and you can further interpolate that using spline interpolation, which I'll explain in the cloud section. And you also have the extended Nirvascan from 1350 to 2150, and these are the fiber, the reflective, and the extended models that you can see here. And you can see these are the OEM models. So we build 3D casing for these, so you don't have to basically look at the circuit board here. it won't be exposed because we are able to build 3D models, 3D case with 3D printed cases for these spectrometers. And here an example you can see for the transmittance model, the 3D case that we've built. So this is 1350 to 2150 with a 12 nanometer resolution, and you get the data at around 5 nanometers. We also have a super extended models that go from 1600 to 2400, which I'm not showing there, but those are more expensive than the standard model. So these units, they comes with a PC software, and you can see this is the general shape of the PC software. In the scan settings, here there is this built-in button here. So once you use the built-in, it uses the reference that is recorded in the spectrometer once it was manufactured in the factory. So they measured the emission of the halogen tungsten lamp, and they stored it in the instrument. So you can just directly go ahead and scan, and you get your I over I0 or I0. But you can also record your own reference. If you put this on new, the scan changes into scan reference. And then you can use the spectral on surface, which I'll show you later, to measure the new reference. And then this jumps to previous, and then you can, and this changes to scan. So you can just scan, and that uses your previous recorded reference. You can just do one measurement at the beginning of the day, for example, of the spectral on, and use that as a reference for the rest of the day. You don't have to do it every time, just one measurement. So previous refers to previous recorded reference, not to previous measurement. It refers to previous recorded reference. Of course, you have to connect the instrument with a USB cable to your computer. So the software would give you different graphs, the reflected intensity, the reflectance function, which is I over I naught, and the absorbance, which is log of 1 over R. And normally for chemometric modeling or machine learning modeling, the absorbance is used. So these are some basic steps in calculating the absorbance or transmittance. So it's pretty self-explanatory here, which I would not spend time on. And here is how to record a reference, which I was explaining there. This is a spectral on surface, which we could also provide. You could buy from us directly. And the spectrometer is placed on this. This is a reflective model. It works only for the reflective model and also for the fiber model, but not for the transmittance model. So measure the reference and then use it in the following steps for measuring the spectrum. So one question that arises is, why do we need an external reference? Why can't we not keep using the recorded built-in spectra reference? And that's the reason is explained in the next slide. So if you go to the scan configuration, you can see there is this scan configuration column 1 that is defined with certain parameters. So spectral range 900 to 1700 with 7.03 nanometer, exposure time 0.635 milliseconds, digital resolution 228. So if you don't change any of the parameters and you keep using column 1, then you can keep using your recorded reference, the factory built-in reference. But if you want to change some of the parameters, especially the ones that are wavelength related, so width nanometer or digital resolution, then you need to record your reference with the same parameters. And you cannot change the parameters and use the the factory reference, because that has been recorded with certain parameters. So as long as you don't change the parameters, you could use it. But if you decide to change the parameters, then you need to record a new reference. Number of scans to average is fine. You can change that and still use the built-in reference. So normally it's 6, but you can even use 100. Of course, 6 would take shorter time than 100. 100 would typically take about 220 seconds to scan. 6 would be only 3 seconds. But there's no problem changing number of averages. But for other parameters, you need to record a new reference. You can also basically create a new scan configuration based on what you want and call it a different name. So we have already column 1 and Hadamard 1 in our database, so which you can use. And I explained to you what the difference between these two is. But basically the default value is column 1. This is a default scan configuration. Here also on the right side, you see we have an app, so you can also communicate using Bluetooth with the instrument, and you can connect to it and make the measurements, and then you can transfer your files to your PC. I'll talk about that a little bit later, how to do that. So one question is, what's the difference between the column and Hadamard scan configuration? So the spectrometer has different frames during the measurement. So in case of the column, each of these columns represent a frame. So you can see in the first frame, the first mirror is turned towards the detector, is on. The other 2 mirrors are off. This example only shows with basically three mirrors. But in the second frame, again, the second one is on, the other 2 are off. And in the third frame, third one is on, the other 2 is off. However, in the Hadamard method, in the first frame, you have 1 and 3 are on, 2 is off. In the second frame, 2 and 3 are on, 1 is off. And in the third frame, 1 and 2 are on, and the third is off. So this additional basically number of mirrors that turn towards the detector produces a bigger throughput and improves the signal to noise ratio. So wide DMD pattern is displayed, higher optical energy will be captured by the InGaAs detector. So, if you have noise issues, if your signals are noisy, you might want to consider going to the Hadamard pattern to do your measurements. Okay, next, you have the overlay function here. So if I go back to the previous slide, under saved scans, you have all your scans there. You can also name your scans here. Let me go back here. You can see file name over here, and then choose a directory, what's the file name, and all of these are saved basically. So if you want to compare some scans together, you can use the overlay and plot them at the same time, and then look at different differences between them or similarities between them. Okay, so now we go to chemometrics and statistical analysis of the spectra. Excuse me. So I mentioned that you need to use statistical analysis to understand the near IR spectrum. It's not so straightforward like the mid IR, where you have high resolution and strong peaks. So these combination and overtones need to be deciphered by some statistical methods. So you have the quantitative evaluation. We use partial least square for that mostly. And you also have sorting applications where we use the principal component analysis and linear discriminant analysis. And then we do the score plot and plot one component versus the other. And we see that there is some different piles and clusters where you can separate different types of material. For example, in case of plastics, plastic type 1 to type 7, they basically gather in different areas, in different clusters. So before we have the cloud service, this work was done a few years ago. I used to use Minitab for doing the analysis. So you can basically make a PLS model in Minitab. And here's an example where I use for measuring bricks in grapes. So I'll talk about that a little bit later. But this, I just want to talk a little bit that software is quite expensive if you, for example, want to buy the Unscrambler software, which is a very complete software by Chemoanalytics. It will be a few $1,000s per year subscription to have that. There's a webinar by Dr. Heather Brooks in this link. We'll send you all these links later when we send you the recording. And you can see that they tried to analyze different wheat samples. All the wheat absorption spectra are along the rows, and the first column has the protein content. And normally they divide the samples into calibration and validation, 2/3 calibration, 1/3 validation, and then they run the software. It has many features, and then do the analysis. But it's quite expensive. Minitab is a little bit less expensive, but doesn't have all the features. Like cannot do pre-processing, for example. You have to do the pre-processing outside of that environment. So let's talk about some of the case studies. The first one is sweetness of fruits. So one of our customers works in France and deals with grapes for wine. So he was very curious to know the Brix content of these grapes, also the pH content of the grapes. So he sent us some samples initially a few years ago, and this is what the absorption measurements from the grapes look like using our Nirvascan. And he measured the actual or gold standard for this measurement. The actual value was measured by a Brix meter that you can see in this case. So we had the actual Brix content for each sample, and we also had the infrared, near infrared absorption spectrum for each sample. And right off the bat, when you look at this spectra, you see there's an outlier. Just visually observe, this is an outlier. So you can remove this outlier. Normally you want to remove the outliers just by visual inspection at the beginning. There are also other methods of removing outliers in statistical packages. Even Minitab has that. So we need to remove the outliers to have more accurate model. So what we normally do is once you see the samples spectra, they are shifted by a DC offset. So you may even do measurement from the same sample, and you see each spectra is shifted with respect to the other by a DC offset. And this is all due to scattering that takes place. It's quite normal in near IR to have this kind of effect. So in order to remove that DC offset, we normally have to apply the second derivative or first derivative. The advantage of second derivative is that the peaks that occur, they are at the same peak as the original raw spectrum in this case. So that would get rid of the DC offset, but it would introduce some noise. So you also need to apply a filter such as Savitsky-Golay filter, which would basically fit a polynomial into a certain window region. So here you can see there is a second degree polynomial that has been fitted here and removes the noise or reduces the noise. So this is a very important operation, second derivative plus Savitsky-Golay. And I'll talk about that in our cloud in more detail. So once we did that, we got, this is a second derivative spectrum, and we did the analysis made a PLS model, and this is the R square 0.87, the RMSC of 0.77 bricks is what we got. Although our model had some holes, basically, so we didn't have values in this 18 to 20 bricks range, but despite that, we didn't get a bad result by doing the model. And our second serious project was the wheat kernels. We wanted to know the protein content and the moisture content of wheat. So first of all, first question is that why do we need to know the protein content? Why do farmers want to know the protein content of the wheat? And simply, the price of wheat is proportional to its protein content. So the higher the protein content, the higher is the price. So you can see the price goes up there. So our customer is in Manitoba, and there are a lot of farmers who want to know the protein content of the wheat they produce. And they have these different, there are these different gold standards, such as HPLC, Dumas combustion method, Kajal-Dahal method, and there's also this grating micrometer, which is quite an expensive instrument, and our customer in Manitoba has it. And this is a $20,000 instrument. So this would just measure the protein and moisture and tell you with a high accuracy of maybe 0.1% what the values are. But the idea was that whether we could use this as a gold standard and we could use the near IR to do the measurements, and that would reduce the cost of the measurement, because our standard spectrometer is nearly about $2,600. And if you have a model that works, then it would reduce the cost, and then the farmers could purchase that. So we tried with different models, 80 calibration, 20 validation. We did 4 measurements from each sample, every time shuffling the wheat kernels to make sure that different grains are measured. And you can see these are the raw spectra. And we did the second derivative. All the DC offset disappears, as you can see here, and they all fall mostly on top of each other. So this is the second derivative, and then the Savitsky-Golay. And then we made a calibration. We made a PLS model using the calibration file, and we made predictions on our validations. And we got a 0.47 RMSC. So here I'm showing that we only used from 14.6 to 16.6, because in this range we had a higher number of samples. We tried it on the whole range, but because in some areas we don't have enough samples, the result of the model was not very good. We need to get a hold of more samples in these wing areas, but it's not always easy to get these samples. It depends on the year and the production and the environmental conditions. So we did the model only for this range, 14.6 to 16.6, where we had maximum number of samples. Now, the other study was to study moisture, or to measure moisture. And why do they want to measure moisture? Is because the storage condition of wheat depends on the moisture. So higher is the moisture and the temperature, the higher would be the possibility of a spoilage. So for this reason, they need to measure the moisture in wheat. So once again, we had 74 calibration spectra, 18 validation. I'm not showing the Savitsky-Golay and second derivative, but again, this was in a region where we had maximum number of samples. And we did the PLS model, and we got the RMSC of 0.34%, which is pretty good. And these are all the predictions. So this was done accurately, and we were satisfied with our modeling, the PLS modeling. Of course, you can use Machine learning also, a lot of our customers who are very interested in machine learning. But one thing that is to be noted is that for a smaller number of samples, say 100, 200, PLS model gives more accurate results than machine learning. If your samples are very large, like 500 plus, then machine learning would give better results. So we used PLS, we didn't use machine learning, but it can be done using machine learning too. So now I'm going to talk about the cloud. This was one primary reason for the webinar, to introduce our cloud and to the operation of the cloud, because it's quite important to use the cloud when you're using Nirvascan. And I explain why. So the cloud is capable of uploading spectra and near IR profiles. You can also plot. You could plot individual spectra and near IR profiles. You could do PCA, PLS, and LDM modeling. You can make predictions. You can do pre-processing, second derivative, Savitsky-Golay. And if you subscribe to it, it's free for 6 months. After you purchase the instrument, you have free subscriptions for 6 months. And there's a small monthly charge of $25 per month after that. Okay, so let me look at the cloud right now and explain the cloud. So 1 second. So we go to profiles, go back here. Let me type this, nirvacloud.ai. Nirvacloud.ai is the address, and this is the main page at the beginning, and I'm already registered here, but for those of you who purchase the instrument, you can go here to basically register. So if I log out, it will just say either log in or register. You could choose register, and then you would enter some basic information, and it will probably ask you the serial number of your device as well, and then you can start using the cloud. So you go to the analysis. First, you go to the analysis, and this is the main page that you'll get. And I'd like to emphasize that there is a feature here where if you want your data to be confidential, you don't want other people to see it, you can use private settings. So the data will only be visible to you and not to the other customers who are using the cloud. Okay, so first thing, for example, you could look at different spectra. Here is like one spectra. You can plot these spectra in high resolution. It looks like that. Or you could use different profiles. Here, for example, let's look at these profiles for protein content. Again, high resolution. You can hide the labels. So different profiles are here that were uploaded by different customers. So the first thing that I want to show here is about these tools here. These tools, averaging tool and interpolation tools, are very, very useful. And the reason is that you may have hundreds of measurements. So let's say you do 4 measurements from wheat, and you have, say, 25 samples. That's 100 spectra already. So how would you want to average that? It's a manually doing it would be very time consuming and difficult. It's possible to take all the absorbances and average them, but this tool will help you to average your results. And it will only do average of 4 measurements. That's the default value, and at the moment it cannot be changed. So if you have 4 averages, you can, and you have 100 measurements, you can do that. So let me show you how to do that. So you click on the average tool, and then you go to the directory where all your files are. So you go, for example, choose files, and then you would select your directory. So let me go to a particular directory and select one set of files. So this one, I go to CSV file. So you can see there are these samples, right? Sample 1, take 1, sample box to sample 1, take 2, sample 1, take 3, and sample 1, take 4. And then sample 2, 4 measurements. So let me choose 10 of these. 1, 2, 3, 4, 5, 6. So I'll go down to 10 just to keep it short. I'll keep it like that. And then I say open. So it will choose all these 40 files, and it's a multiple of 4. So it will basically average the first 4 and put the result in a horizontal row in a spreadsheet. Then you say upload to calculate. And he calculated and export the average data. So this is the average data. Okay, so let me look at downloads, and here is the average, Wheatbox 2 averaged. So let's look at this, because we had 40 spectra and 4 of them was from each sample, so we should have 10 averages. So the row 2 is the average of the first 4, and row 3 is average of the second 4, and so on. So these are from 2 to 11 are the spectra. So it does all of that for you. And these are the wavelengths. 901 point, remember I said it's about 3.5, something like that, the difference. So these are the wavelengths. The first row is the wavelength, and the second to 11th row are the absorbances. So this was one feature, which is quite important. And the second is the interpolation tool. So this would interpolate your basically values at 2 nanometers, your wavelength values. So, and I will also explain right after doing it why that is important. Why is interpolation necessary and important? So I'll go to choose files, and then I go to the same file that I just averaged. So I go to downloads, and I choose this file, box 2 averaged, and open it and upload to calculate. It'll give you export interpolated data. It exported that data, and then I go to downloads. I go to downloads, and I see interpolated. So let's take a look at that. And now you can see the X has the basically wavelength range has changed into interpolated 900, 902, 904, all the way to 1700. Okay, instead of those fractional numbers. So why is this important? We need to talk about why is this important to do. So let me show something here about the wavelength issue. So I'm going to go to the manual of this and do a search under spline. So those values you saw was a spline interpolation. So if you look at this, you'll see that, let me make a zoom a little bit. Yes, so if you have several devices, the wavelengths are slightly different based on wavelength calibration. 901.81 here, 901.56, 905.708, 905.474. So this is not good, because if you have a model and you want to use that, you want to use several devices that you purchased with the same model, you need to have a uniform wavelength scale. Otherwise, this will be a degree of uncertainty, another variable in your model. So you need to make sure that the wavelengths are the same for different instruments. And then somebody could say, okay, I don't have many instruments. I have only one instrument. Why do I need to do this? And the reason is, if you do subtraction, the interval between, say, 901.8, 905.7, and 901.5 and 905.4 is different. No, we're not considering the second device, sorry. We're talking only about one device. The different interval, 901.8, 905.7, 905.59, this interval is different from this interval. So the interval between two consecutive wavelengths is constantly changing slightly. And that would make the second derivative operation inaccurate. So for this reason, you need to apply spline interpolation, which our button, tool button in the cloud would do, and we do it at twice the interval, or half the interval based on the Nyquist theorem, and you would just get, for device 1 and device 2, you get, first of all, the intervals are the same for each one particular device. The intervals are the same, and also they are same for the different devices. So for this reason, it's very important to do the spline interpolation. I hope that is clear. So next, I'm going to try to show more features on the cloud. So we did our interpolation, and we have the file here. Let me show the file one more time. Average, yeah. So what you need to do now is also to make a column here. So make a column here, and let's say we are measuring protein, and this has to be protein content. So you can put the protein content in the first column. So that's quite important to be able to upload into the cloud on the, basically upload the profile. So here I'll show you an example. Calibration, I've already done that. So I'll show you what it looks like. So this one has not been interpolated, but it has all the protein contents here. So all the protein contents are in the first column. And normally what we do is that, let's say we have 100 samples, we divide it into 2/3 calibration, 1/3 validation. And we organize them based on, increasing ingredient. And then we would choose every third one for validation. So we can separate the full file 100 into 66 calibration and 34 validation. So this is our calibration. You can see it needs to have the protein in its file name. So this is the name, VK Cal 990 sort and protein, and then dash whatever. But the name should contain protein, which is in the first column. If it is moisture, then the middle part should be moisture and moisture. And we also have for the validation, this is the validation. Okay, so this is the validation. So it is only 38. Okay, so once you upload the validation and calibration on the cloud, you can look at it. So I'm going to show you here, for example, this file, December 12, 2022. So you have a calibration file, you have a validation file, and let's look at it on the cloud. So this is our calibration file in high resolution. And then this will be our validation file. Validation in high resolution. All right. So the next question that is important is, so, okay, we uploaded the calibration validation. So how do we know what are the optimized parameters we need to use for our PLS model? The number of components of PLS model, and also the number of Savitsky-Golay widths. What widths should we use for it? So we have a feature that does that for you. So you could select these two, calibration, validation, and then you would go here and say, get optimized parameters. So it will tell you that the optimized parameters are 9 and 29. If I choose something different, there will be another parameter which I want. There are another file that I want to use. This one I wanted to use. The WheatK val IP stands for interpolated. This is the validation. This is the calibration. So if you choose these two, get optimized parameters, it'll say 3, number of components 3, and window length 27. So that will tell us what the values are. All right, so that's pretty good. So now we want to start doing our PLS model. My idea was to show you how to make the PLS model on the cloud. So you would go add, you click on add, and then let's give it a name. Let's say webinar test 1 is the name of the PLS model, webinar test 1. And number of components we already found is 3. So we put 3. And minimum, maximum, we don't usually use the first 50 nanometer and the last 50 nanometer from 900 to 1700 because those readings are prone to temperature changes and could vary and affect our model. So it's safer just to throw them out, the first 50 and the last 50. Just use 950 to 1650. And then you leave the calibration spectrum, and then you would choose your calibration file. So your calibration file, let's look for it. It was on moisture. Yes. I think this is the calibration file. ASP December 12, 22. That's it. And then click on apply SG. Window length we already found is 27 is the optimized value. Polynomial order is always 1 higher than the derivative. So derivative is second derivative, so this should be 3 and second, and then we save it. All right, so you see this is our model, PLS model. It already tells us that the RMSC is 0.48%. So this is you can hide the label. These are the model from 12 to 14.6 for moisture. And next, we also have to apply the same Savitsky-Golay to our validation file. So we add this, and then we call it a webinar test 1 val SG, for example, whatever name, just we can recognize this, that this is the validation with SG27. So window length should be 27. We increase it to 27. Polynomial order 3, 1 higher than the derivative. And the cal profile, we go back and find that, the moisture file. It's right here, val IP moisture. So we select that and we save it. Okay, so once we save it, we can take a look at it. This is the model, or this is the Savitsky-Golay applied to the validation spectrum. And then we come to our PLS model, and now we want to make predictions. So we just click on the model. This is our model. And down here, we look for the validation, which was subjected to the Savitsky-Golay. So we would select this, and then we go down and say, apply the model to predict. So here, we got an RMSE of 0.36. This is RMSEV for validation. So our predictions are also given. This is the R square value, 0.637. These are our predictions, and you can export the predictions to an Excel file. So let's look at the Excel file of predictions. So if you click on it, you'll see that these are the true values that were measured by that grating micrometer, and these are the predicted values. So this is how you do the PLS modeling, basically. You also talk a little bit about PCA modeling or LDA modeling for sorting, for example. So one thing that is important in case of the PCA or LDA modeling is that you have to, let's say you are doing plastics, you want to do a PCA model of plastics, you have to make different files for each type. So HDPE is a type of plastic, is type 2 plastic. So I put all my HDPE plastic spectra into one file and I call it HDPE type 2. So you would basically put all of these, you upload all these profiles of different types on the cloud, and then you can go to your, for example, LDA model, add LDA model, give it a name, number of components, usually 2, and then you could select all those things that you have measured, different plastics that you have uploaded. You can select several of these, and then you would save it, and it will give you a PCA or LDA model. So let's look at the LDA model, for example. LDA model for classifying plastics is right here. So you can see there are 1, 2, 3, 4, 5, 6 type of plastics here, and they are all clustered into different regions. So this we can use to identify a new type of plastics. So you can check one of the new type of plastics and ask it to identify, and it will show you a square. Where is it falling, the new plastic? And depending on where it is, it will be identified as one type of plastic or the other. Excuse me. So this was some demonstration of the cloud. I think I spoke about maybe 25 minutes on this. So I hope that this will give you some idea of how to use the cloud. For those of you who already have the instrument or are considering to purchase it, it could do predictions, quantitative, and it could also do sorting. This I already explained. What is the need for a spline interpolation to remove these basically wavelength differences and also the interval differences. So I don't need to explain that again. And also, you also will find that if you have several instruments, even though you did your spline interpolation, if you built the model with one and you're using the other to measure, you find there will be some problems, some discrepancies, and it would not give you accurate readings. So here we have 2 spectrometers. We built the model with one and we measured with the other, and you have a poor RMSCP, 0.209, and 27 of the predicted values were out of a spec. So the way to deal with that would be to use a slope and bias correction. So you would plot each predictions, so predicted versus real, and calculate the slope, and calculate the intercept, and then you plug it into this formula, which contains the 2 slopes and the 2 intercepts, B1, B2, and 1, M2. And after you make these corrections to your predictions, then you can recalculate RMSCP, and now you see it's been reduced to 0.07 and 0 out of spec. So this is another issue that you have to deal with. All right, so enough of the cloud. We have about half an hour left here, so I'm going to go through different applications. So different case studies. So here's one case study where we had to look at different fabrics and with the Nirvascan, and the supplier told us that one of them is different. It has a different ingredient as compared to the others. And we could see just visually that sample number 7 was different. has an extra peak in here that other samples did not show. So it's an aromatic ingredient, toluene, that this particular sample had that the others didn't have. And we measured the polyester and polypropylene content of these samples. We also use it for detection of fake masks. So there are the M3M masks and 95 that you can see over here. So when we did the spectra, we saw that the 3M mask contains a CH3 peak. Polypropylene has a CH3 bond as a distinct identifier. So this does not show in any of the other masks. So this way you can detect fake masks. Very important applications. I talked a little bit about it for plastic identification. And right now in the plastic recycling companies, workers are sorting different types of plastics one by one. But in future, or maybe it's not even implemented now, you could use a hyperspectral camera to look at different types of plastics and also locate where they are. So basically, once you have identified different type of plastic and their location, a nozzle could blow air and separate them into different bins. So there won't be a need for workers to manually separate them. Here you have the plastic recycling model, or LDA model. And we define certain areas around these. So if a new test subject, you can see in the black square, falls in the circle, then we identify it as that particular type of plastic. So plastic number 2 in this case. So we had before an app that could communicate with the cloud, and you send the spectrum, the cloud runs the model, identifies the plastic, and sends the result back to the app. But unfortunately, at the moment, this app is not working. We are trying hard to fix the issue, the communication issue. So we'll make an announcement whenever this starts to work again. But you can still identify your plastics or different things you want to sort on the cloud. So it's just not the real-time app. So I already talked about uploading different spectra. So here's different applications. Some customers, they like to do some medical studies, like possibility of detecting Zika virus in mosquitoes. So there is a need for a rapid and affordable test method for pathogen detection, because insect bite is a problem for global spread of viruses. And near IR is a really good technique. You can measure from the head and thoraces of the mosquitoes, and basically identify, if you have a model, you can identify if the mosquito is carrying the disease or not. There was a study before, and chemometrics could identify with 92.5% accuracy. The gold standard was PCR, the polymerase chain reaction, which is the standard method. So for processing 100 mosquitoes, it took only 50 minutes using an IRS. And if you wanted to do PCR, it would take 2 full days. So pretty useful. This is our transmittance model with a cuvette, and we had a customer who sent us some liquid mixture for production of fluorodeoxyglucose, which is a radiopharmaceutical used in medical imaging, and wanted to check the concentration. So we tried with the Nirvascan. And one thing we found is that there was no signal past 1373 with the 1 centimeter cuvette. So we used a narrower cuvette and reduced the size to 3 millimeter. And all of a sudden, there was another peak past 1300. So for some samples that have high amount of water, the 1 centimeter is not a not a suitable cuvette to use. And we must use glass cuvette, not plastic cuvette, because plastic has some absorptions in the near IR in 900 to 1700. So sometimes you need to use a thinner cuvette to get proper signals. We couldn't really measure the concentrations. It seemed that the detection accuracy was not good enough for this measurement. But here is another example where another customer sent us detergent samples, and we could measure from the 1 centimeter cuvette, and there was no need for using a thinner cuvette. There was also crude oil analysis. Customers send us different crude oil samples with a 1 millimeter cuvette. These are very viscous. And we found that the more viscous they were, the steeper was the slope of basically the absorbance intensity. The absorbance value was very steep at the beginning, and our 2 spectrometers, this is a general absorption spectrum of oil, and this is our standard model, this is our extended model. So it can measure this spectrum in these areas. Another application possibility of detecting viral diseases using NIR. So at the moment, there is a big outbreak of viruses that are basically creating a lot of issues, such as coronavirus. Everyone knows that, West Nile virus, Ebola virus, and conventional methods such as PCR, it takes a lot of time to do the measurement. NIR is a fast, non-invasive, non-destructive, inexpensive method that does not require sample preparation and is very much needed to do a quick test. And samples of the skin or parts of the body have water, melanin, and other compounds, and they are present in sufficient quantities to affect the transmission in NIR region. So one study was done by these Japanese researchers where they were looking at the flu virus using the nasal fluids from different patients, and they used via near-IR spectroscopy from 600 to 1100 nanometer and used the PCA and SIMCA sorting models to distinguish between 35 non-influenza and 34 influenza patients. And they managed to separate them using NIR, the non-influenza from influenza patients. So this was a very useful study. Of course, they had to dilute the samples tenfold, and it was quite successful in separating non-influenza from influenza. However, it could not separate the 2 types of influenza. The influenza and RSV infected could not be separated from each other, but then you could also separate them if you take temperature into account, or maybe you could use machine learning to separate these influenza and RSV infected diseases. Okay, so let's move on to fiber. The fiber model does not have an internal source, and here I'm measuring the emission of a halogen tungsten lamp, which is quite powerful. I think it's about 50 watt. So you can just use a fiber and measure that spectrum. Of course, you need to use the near IR fiber, not the quartz fiber, which is only used for UV. But typically what we use the fiber model is for by using a reflection probe. So reflection probe has 2 inputs and 1 output. So input with the linear shape would go to the spectrometer. The other input with the circular shape would go to the light source, a 5 watt halogen lamp. And then the the output would go first to measure I0 from a spectral lawn surface, and then keeping the geometry the same, you would just replace the spectral lawn with the sample and measure again from the sample. And this way you can measure the absorbance. So measure I0 with the spectral lawn, then measure I from the sample, calculate I over I0, basically, or minus log of I over I0, or log of 1 over R. And then you can do chemometrics on the absorbance. Here's also another model where if you don't want to touch a sample, there is this 5-watt external lamp called DRP1. It has a collection lens at 8 millimeter distance. So you can, not without touching the sample, you can trigger this lamp by electronics. You see these wires are triggering it. So once you press the scan, the lamp would come on for a few seconds, and then the fiber optic, the lens collects the scattered light, focuses into the fiber optic, and fiber optic will go to the spectrometer. So here I'm measuring from the wheat kernels. First I measure with the spectral lawn, the reference, then without touching anything, I'll replace the spectral lawn with the wheat samples, and you can see the absorbance of wheat right here. There's a video here which will send you, if you want to watch in more detail, learn more about it, you can check it out. There's also a proposal for a flow system. If you want to measure a soft drink in a factory, for example, there's a cell here which is offered by the company Avantes microflow cell. It has two inputs. It has an input for the source and a sink. So this is where the liquid runs, and it has a fiber optic input and output. So this one would go to the lamp, and the output would go to the spectrometer. So you can measure it as the liquid is flowing. What is the content? For example, the sugar content of the liquid. Here is the app. So the app is compatible to Android and the App Store or iOS. You can download for free from Android, from Google Play, or from iOS. So I've demonstrated a video here how to run the app. And then after you measure, all the information will be in your phone, and you could connect it to the computer. If you have Android, you just connect it with a cable, and it will appear as an external drive. You can look under Documents, and in the Documents folder, you find all your CSV files. If you use the iOS, it's slightly different. How to use, let me stop this for a second. Pointer options. Okay, so if you have the iOS, then you need to use iTunes. So you need to basically connect your phone to the computer and your iPhone to the computer, and then open iTunes, and then you will see there is encircle the small smartphone sign, and you get a folder called ISC and IR scan where you can see all your files in there. So it's slightly different for iOS as compared to Nirvascan. And by the way, I should just say that the PC software is only available for Windows, not for iOS. But the app is available for iOS and Android. Nirvascan in literature, we have some publications if you want to check it out. And the most important paper was by these Australian researchers evaluating low-cost portable near-infrared sensors for rapid analysis of soils from southeastern Australia. And they compared the performance of Nirvascan with another portable spectrometer based on FTIR and two lab spectrometers, expensive lab spectrometers, and they found that Nirvascan is very competitive and gives good result, especially for total carbon of the soil. It gives very good results comparable to the other spectrometers. And this one is for evaluation of seafood for decomposition, which seafood is fresh, what seafood is not fresh. So by using the PCA modeling, they could find that. This is by some American researchers that they did this paper. So finally, we come to the conclusion. In short, what did we learn from this webinar, or what were the highlights of the webinar, basically? One, that Nirvascan model reflective showed promising results in many different industries, such as food, textile, plastics, health monitoring. The transmission model, we demonstrate that it would basically work for liquid solutions such as detergents, but in some cases, 1 centimeter thickness cuvette is too thick. You need to use smaller thicknesses to be able to see the full signal. I showed that for one of the case studies. The fiber model with the DRP1 external source could be used to measure at 8 millimeter distance without touching the sample, and you can also use the reflection probe to measure from different samples. And use of chemometrics such as LDA model and PLS is highly recommended. Moisture, protein, and bricks were measured using PLS modeling for grapes and wheat. Cloud service, we talked about it, we demoed it. It's available for use free of charge for 6 months if a Nirvascan unit is purchased. And after that, it's $25 per month charge for using the cloud. Plastic sorting can be done using LDA on the cloud, and we saw that we could see different type of plastics separating from each other. And if you notice, there were only 6 out of 7 present. Is because the LDPE and HDPE, low density polyethylene and high density polyethylene, they have the same spectra in the 900 to 1700. But if you use the extended version, there is a peak at around 1800 that is different from the two of them. So that's why when I was showing for the standard method, the standard model, the score plot, I did not plot LDP because they will be the same as HDP. But the extended one would work better in that case. Finally, crude oil spectra were measured using the transmittance model, and we found that there is a steeper slope of the absorbance for the more viscous samples as compared to the others. So with this, we come to the end of this webinar. Talk about 1 hour and 17 minutes. And we leave a few minutes for questions if anyone has any question. We also send you a feedback form to fill out about any suggestions you might have. I thank you very much for listening to this webinar, and I hope that it was useful. And feel free to message me if there's any question. Again, my email is given here. So at this point, if you have any questions, please either unmute yourself or you can type in the chat box. So if you have any questions, please let me know. Are there any questions? Okay, seems there's not. If you think of any other question in future, you can still, when you receive the recording, you can look at it again. If you come up with any question, Feel free to email us, rmani@alliedscientificpro.com. I can also send this in the chat. So I'll be glad to answer any inquiries. Once again, I thank you very much for your participation in this webinar, and I'm looking forward to hearing back from you. Thank you. Bye.